Welcome everyone to the 11th lecture of Introduction to Deep Learning. Let's start with the lecture 10 recap. So in the last lecture, we saw classic architectures for convolutional neural networks. We started with the small LaNet, which was used for digit recognition, therefore to classify an input image into a set of 10 classes from 0 to 9. So in the image, there was the handwritten digit, and the convolutional neural network was in charge of classifying the content of that drawing. So what digit was represented in the drawing. And we saw the classic convolutional neural network architecture that is actually still now used nowadays. The classic convolution pooling. So this series of feature extraction plus feature selection or feature aggregation, and a final set of fully connected layers that maps the feature map into the classes that we have in our output. And as we go deeper, we see that the width and height of our activation map goes down, therefore the spatial size is reduced, but the number of filters or the depth of our activation map is actually increased. So we're condensing spatial information into this set of channels. And we saw how this small network with just 60,000 parameters can be evolved into, for example, AlexNet, which was the classic architecture that was used to beat the results on image classification on the ImageNet challenge. And this architecture follows the same paradigm, the paradigm of convolution pooling. But of course, it has an output which is now of 1,000 classes, so a much more complex task. And therefore, it needs to have a much larger set of parameters. So many more weights are going to be learned inside this neural network with backpropagation. We then moved to the VGGNet, which is an architecture that was initially designed to simplify the architecture design. So before in AlexNet, we had different kernel sizes, different strides, and VGGNet proposed an architecture that was simple, still followed this convolution pooling paradigm, but only use 3x3 convolutions with stride 1 and 2x2 max pooling. Again, as we go deeper into the architecture, the spatial size is reduced and the number of channels is increased. And with these kind of ingredients, we can create any VGGNet that we want. For example, VGG16 has 16 layers that have weights, and we now have, with these 16 layers, 138 million parameters. So we're talking about a larger network. So of course, this network is large, but the simplicity of designing a VGG16, VGG19 network and not having to think about what kind of convolutions we're going to use, what kind of stride we're going to use, made it actually very appealing. We then presented the residual block, a very important milestone into making networks deeper and deeper and still trainable. And the key insight was inside, for example, 2 layers. So we have this processing going from the output of layer L-1 to the output XL+1. Between this processing, it can happen that gradients vanish or we do a computation that is not optimal for the neural network. And what the residual block does is it creates this shortcut that bypasses all of these operations. So if anything goes wrong inside these 2 layers, we will always have this shortcut, this skip connection, that allows us to skip all of these operations and have the same output that we had before these 2 layers already set here after these 2 computational blocks. And this also helps when computing backpropagation when backpropagating gradients, because we have this direct highway for the gradients to flow. So if the gradients would be stopped here for any reason, we still have this highway where the gradients can flow. And with these residual blocks, we saw that we could train deeper and deeper networks, and the performance never decreased, but only increased. And we finally saw the inception layer and how to use the one-by-one convolutions to reduce the number of multiplications that we need to do when we are applying different types of convolutions with different kernel sizes. So the key insight of the inception layer is not to choose one type of convolution, but to apply all of them, and then allow the network to choose the best output for the task at hand. But of course, computing one-by-one convolution, 3-by-3 convolution, 5-by-5 convolution, and max pooling, and then concatenating all the output would mean that for every layer, we would have a huge output, which would mean huge number of multiplications on the next layer. And this is why we use one-by-one convolutions to reduce the depth of the output, the depth of our feature map, so that we can apply these operations in a cheaper way. So today we're going to cover two different topics. We're going to start with a brief introduction on the importance of transfer learning and what do we mean when we talk about transfer learning. So this is especially important in computer vision. We have always discussed our models, our convolutional neural networks, for example, and training them with backpropagation, with optimization, assuming that we have available a set of annotations. Our ground truth is readily available, and we have millions and millions of images to train these huge networks, these inception nets or these VGG net. Sometimes this is not the case, and training a model from scratch can be difficult. For example, we don't have resources, we need large CPUs to train these models, or we don't have data. Usually, this second case is more often the case because it is actually very expensive to manually annotate your own training data set. So imagine annotating millions and millions of images so that your network can learn to distinguish between cat, dog, chair, car, etc. So the question that transfer learning poses is, why not reusing already pre-trained models, models that are trained on a similar task? And so we can borrow something from those trained models, something from those weights of the trained neural network to perform better at the task at hand. So we start with the concept of these two distributions, the distribution P1 and the distribution P2. Now, P1 is our large data set. Imagine there is a data set online that is really, really large, millions of images, and these images are annotated for a certain task. And then we have the distribution P2, which comes from a small data set that we have annotated ourselves, and that actually targets a slightly different task. So the task that P1 and P2 target is different. Now, what we want to do in transfer learning is we want to use what we have learned from our large data set that was created for one task, and we want to use that knowledge for the other task for which we only have a small data set. And usually what we mean with using that knowledge in convolutional neural networks, we mean using the features that we have learned with the large data set and transferring those features, transferring that knowledge to the small data set. And if we look again at the feature extraction that we saw before on images, so the feature extraction that the CNN does automatically, and how we go from low-level features to mid-level features all the way to top-level features, which are already almost object parts, we can imagine that transfer learning can really leverage the low-level feature extraction, for example. Even if the two tasks are very different, the low-level feature extraction is going to be very similar if the input are still RGB images. And therefore, we can really leverage transfer learning for images from one task to the other. Usually the case is that we pre-train our neural network on a large dataset, such as ImageNet, which is used for image classification, and then we fine-tune it for detection, segmentation, or any task that we want to solve. So how do we, in practice, do transfer learning? Let's see an example of a network that is trained on ImageNet. Now, our network contains a series of convolutional layers, pooling layers, and finally, the set of fully connected layers that maps our feature map into our 1000 classes, the 1000 classes of ImageNet. Now, what we're really interested in are the feature extraction layers, the convolutional layers that detect all those simple edges, the first low-level features, and then put them together to create simple geometrical shapes, and finally put all of this together to create parts of an object, for example, a wheel or a window if we're doing car detection. These are the kinds of weights that we're going to be interested in keeping or in using as a starting point with the concept of transfer learning. So what we can do is we can delete, we can change only the decision layers. So in this case, for this particular convolutional neural network, we have a last decision layer which maps a 4098 vector into the 1000 classes of ImageNet. But it can be that our task doesn't contain 1000 classes. We might still want to do image classification, but now we have C classes, where C is any number that you want, depending on the task that you want to solve. So in this case, what we can do is we can train only this last fully connected layer. Only this layer that maps the 4096 vector into the set of classes that we want to classify our image with. So of course, if we had 1000 classes before and this doesn't work for us, we're going to have to completely change that fully connected layer and train it from scratch. But the nice thing about transfer learning is that we can reuse all those previous layers, we can completely freeze them so that with very few data, we can focus on training only that last layer. Now, of course, if the data set that we have, the annotations that we have, are a bit larger, we have a data set that is big enough, we can actually train more layers. For example, we can train all the fully connected layers. So we can either start from scratch and train those layers from scratch, or we can use a lower learning rate for the last, or let's say the first two fully connected layers, so these ones that map the features to this 4096 vector. We can train those with a low learning rate and then train the last layer with a higher learning rate. So depending on how large one's data set is, one can train more or less layers and going all the way to even the first convolutional layers if the data set is large enough. So when does transfer learning really make sense? Well, first of all, we need to make sure that the two tasks that we're dealing with, the task from which we have the large data set, T1, and the task for which we have the small data set, T2, we have to make sure that they have the same input, especially if we want to use the low-level features and one is dealing with an RGB image as an input and the other has, for example, a CT scan as an input. It is obvious that the features that we need to understand both types of images are not going to be the same. So it's really important to have the same input for both tasks. Of course, transfer learning also makes sense when you have more data for task T1 than for task T2. So you need always to start from a really large data set in order to pre-train your network. And finally, when you're sure that the low-level features for T1 can be useful to learn T2. It can be that the two tasks are so different that even if they take the same input, not even the low-level features can be reused from T1 to T2. Okay, so up until now, we have discussed many topics in this introduction to deep learning course. And we think you're now ready to perform, for example, image classification on any dataset. You're ready to choose your own architecture, to know how to train your neural network, know exactly how the optimization works and how to monitor your training process. And so you're ready to tackle the task of image classification. You're also ready to design your own architecture or make small changes to existing architectures. And you understand the architectures that are out there, the common names of ResNet, InceptionNet, you know exactly how they work. And finally, you're also ready to deal with other problems. For example, semantic segmentation. You're ready to design a fully convolutional network and use a pre-trained network for image classification, convert it into a fully convolutional network, and train it, for example, for semantic segmentation. But there is one thing that we haven't discussed, and these are how to process sequences. And this is why we will cover in the remainder of the lecture recurrent neural networks. So in processing sequences, we use recurrent neural networks because we have a sequence as an input or a sequence as an output or both. That is, we don't have the classic input-output that we have been talking about. For example, one input, that is an image, and one output, that is a label, for example, cat, dog, or chair. But now, with recurrent neural networks, we're going to have a sequence of inputs. So our input is not going to be one element, but a sequence, so a set of elements. And the cool thing about RNNs, or recurrent neural networks, is that they are extremely flexible. So before, what we have seen so far is this one-to-one mapping between the input, for example, an image, a set of hidden layers, for example, the set of convolutional layers, pooling layers, and finally, an output, which is also one element, for example, a label. This is the classic structure that we have been seeing so far with neural networks, for example, with CNNs for image classification. But with RNNs, we can do other types of mappings. We can go from one input to many output. And for example, this is the case of image captioning. So in image captioning, we want to input an image and we want as output a sentence that explains what is happening in that image. For this, we need to have this one-to-many mapping. And therefore, we're going to use recurrent neural networks for that. But we can also have a many-to-one mapping. So having a sequence as input, as we have down here, by having only one output. This would be the case for language recognition. You input a series of sentences and you get as output the language in which these sentences are written. But of course, with recurrent neural networks, we can also do many-to-many mapping, as is the case for machine translation, where both the input sentence in one language and the output sentence in another language are sequences of words. And machine translation requires that we first read a little bit of the first sentence in order to understand the full meaning of the sentence, and then we translate it. This is why this sequence here is more to the left than this sequence here, if we take into account that the x-axis would be, for example, the time axis, right? First, we would read our sentence, and then we would translate it. But we can also have many-to-many mapping in which we want to have an immediate action. For example, in the case of event classification, we have a series of video frames as input, and then we have a series of labels as output for every frame that tells us what kind of event is being depicted in that frame of the video. So recurrent neural networks are extremely flexible, and this is why we're going to cover them in this lecture, and we're going to see how to perform this operation here. So what are these hidden layers inside a recurrent neural network? So the basic structure of the RNN is going to be this multi-layer recurrent neural network, where we have here our sequence of inputs and a sequence also as an output. So of course, all of the cases that we have presented in this slide can be summarized with this structure, where we have a sequence in the input and also a sequence in the output. And then in the middle, we're going to have all these green boxes, which represent the hidden states. And the hidden states evolve in two ways. One is in the time direction, and the other is in the depth. So of course we can have several layers of our recurrent neural network, and all of these layers are processing our sequence, and therefore they have this horizontal connection, which is the connection in the temporal domain. Now, of course, these hidden states have their own internal dynamics. So look at all of these connections that have the temporal connection, but also the connection in depth. And therefore, these models are extremely expressive. So how is the basic structure of an RNN? Now, the first thing that we need to have this notion of time, or this notion of a sequence. The fact that we're not processing only one input, but we're processing a sequence of elements. And so we will have this kind of structure where we have still the input here below, xt. So now I'm pointing you to the fact that we have added this t subindex here, which indicates that this input is a sequence, and therefore we're going to have several elements that are going to be inputted to this recurrent neural network, and these elements are going to have a timestamp. So in this case, we're going to have the input xt, and we're going to have the output ht. And here in the middle, we're going to have the bulk of the processing of the recurrent neural network. So this is our hidden state. And therefore, we have here a very crude simplification of a recurrent neural network. A network that processes the input. This is the first thing that the neural network does. It takes the input, the current input at time t, and it processes it with a series of weights, theta. And then we have the previous time step. So this is the hidden state of the time step t-1. So on the one hand, we have the current input xt, and on the other hand, we have the hidden state at time t-1. And these two sources of information, right, the past information that is condensed in the hidden state at-1, and the current present information that is coming from input xt, these two are going to be processed in different ways with two different sets of weights, which are theta c and theta x. And once we process all of this information, we're going to condense it into the current hidden state at. And from the current hidden state, we're going to be able to infer the output. So again, remember that we have these two parallel processings, the processing of the previous hidden state coming together with the processing of the input. So we have to merge these two sources of information. Now, these parameters theta x and theta c are actually the parameters to be learned, are the parameters of the recurrent neural network that we're going to find out using backpropagation. So when we train the neural network, we're going to find out what is the value for these parameters. Now with this current hidden state at, what we're going to do is we're going to predict an output. So let's imagine that we're doing machine translation and I have a sentence as an input here, and I've already decoded some of the words, so the content of the sentence can be found in at-1. And now comes a new word. The new word is xt, and now I have to put together this knowledge in order to translate the current word and have an output ht. And of course, this is done with yet another set of weights theta h. Now, it is important to note that we haven't written any of the nonlinearities. So in this formulation, the nonlinearities are ignored, but of course we have nonlinearities also inside recurrent neural networks, as we will see in a few slides. Now, the cool thing about neural networks is that the parameters that we're training, the parameters that we are learning with backpropagation, are the same parameters for each time step. So for x1, x2, x3, all the way to xt, all of the inputs are going to be processed with a set of parameters theta x. And all the previous hidden states are going to be processed with theta c. And all the output words are going to be created from the hidden state and the set of parameters theta h. And this is what brings generalization to recurrent neural networks, the fact that these parameters are the same for each time step. Now, if we were to unroll this recurrent neural network, we would get to such a representation. A representation in which we start from the first element of our sequence, x0, we feed it into the hidden state, and we output the first word of the sentence. And from then onwards, what we do is we have, first of all, a connection between the previous hidden state and the current hidden state, and a connection between the current input and the current hidden state. Right? These are the two sources of information that I'm processing when I have a recurrent neural network. And from the current hidden state, we predict the output. Now, the important thing to note is that we have, again, the same function for the hidden layers. Therefore, x0, x1, and x2 are going to be processed with exactly the same weights. And of course, what changes are the hidden state that has kind of condensed all the information from all the previous inputs of the sequence, and therefore the combination between the previous hidden state and the current input is what actually changes the output. But again, the parameters are the same for all the time steps. And another important thing of recurrent neural networks is that we have a lot of dependencies. So the output at time step 2, the output h2, depends not only on the input x2, as is the case for example, for image classification, right? You have your current image, there is a cat in the image, and therefore the label cat depends heavily on the image, but doesn't depend on anything else. Now here, it is slightly different because h2 depends not only on the input x2, but depends also on the input x1. Of course, the translation of a word could change depending on the concept. And therefore, h2 now depends on all the previous words, all the previous inputs of the input sentence. Now here we have another representation of this unrolling of the recurrent neural networks. So we're going to represent recurrent neural networks as feed-forward networks. So in this case, what we have is the input at time t. We have x1 time t and x2 at time t. So in this case, our input has two dimensions, x1 and x2, and the timestamp is t. Now these two elements are processed by a series of weights. So imagine that each of these inputs is processed by a node in a feed-forward neural network, and then we need to have all the connections that lead to the next layer of the neural network. And these connections happen with a series of weights W1, W2, W3, and W4. Now, in the next time step, we have again two nodes, which are processing x1 and x2. But now they are processing x1 of t plus 1 and x2 of t plus 1. Therefore, we see this connection with w1 all the way to w4 between time step t and time step t plus 1. Now, the key insight of recurrent neural networks is that the connection between t and t plus 1 is the same as the connection between t plus 1 and t plus 2. We're going to use exactly the same weights w1, w2, w3, and w4. Now, this is the key insight, right? We're going to use exactly the same weights no matter how many inputs we have in our recurrent neural network. So one way to represent recurrent neural networks as feed-forward networks is this way, in which we clearly see that we're using exactly the same weights. Now, this view is especially helpful when we want to understand backpropagation through a recurrent neural network. Because now, if we start from one node and we want to backpropagate, with feed-forward networks, what we would do is we would compute the derivative and we would use the chain rule. But now, what is the derivative with respect to W1? Of course, this is not so simple as with feed-forward networks because we have W1 pretty much everywhere in our recurrent neural network. Therefore, we're going to use the chain rule as we did with feed-forward networks, but we're going to have to backpropagate all the way to T0 in order to exactly establish the derivative with respect to, for example, W1. So in order to compute the update for that particular weight, we're going to have to add the derivatives at different time steps for each of the weights. We're not going to go into more details into how to actually compute by hand backpropagation through an RNN, but we want you to get this intuition that a derivative is not so straightforward to compute as we had with feed-forward networks, because the weights appear in each of the time steps. And therefore, the derivatives are going to have to be combined. The derivative between the different time steps are going to have to be combined for each of the weights so that we can perform the backpropagation and train a recurrent neural network. One of the most important problems that we face when using recurrent neural networks is the problem of long-term dependencies. So let's imagine that we're given the task of reconstructing a sentence. And in particular, we have to make the prediction of this particular word in the output. There is no word in the input. We don't know what the word was there. So we have to infer what that word could have been in the original sentence. And let's imagine that the original sentence was, I moved to Germany, then a parenthesis with some sentences in the middle, and at the end, so I speak German fluently. Now, of course, if German is the word that we have to infer here, we have to go all the way back to the beginning of the sentence to understand that this person moved to Germany, and therefore the most likely output is that the person speaks German fluently and not French or English or any other language. This means that this output here at t plus 1 is going to depend on the input x0 and x1. And it could be that the distance between t plus 1 and 0 is really large because there are many words in between that have nothing to do and don't really help in inferring that this word that should be predicted is German. Now, when this happens, one of the effects of these long-term dependencies, or one of the hard things of these long-term dependencies, is to keep enough information in these hidden states from x0 and x1 so that at t+1 we can predict the correct output. This is extremely challenging. So let's see why. Let's look at again at our simpler recurrence. We have the output of the hidden state AT, which is predicted from the previous hidden state AT-1 and the current input XT. And we have the set of weights for our neural network theta C and theta X. Now let us forget about the input for a second. Let us consider only the dependency between AT and the previous time step AT-1. If we unfold this recurrence, we will reach A0, the first hidden state at time step 0. And we will see that in order to reach AT, we had to multiply our set of weights theta C t times. Therefore, we're going to have here theta C to the power of t multiplied by the input hidden state at time step 0, so A0. Now, we can see here that what we're essentially doing is we're multiplying the same weights over and over and over again. And what can happen here is that if the weights are very, very, very small, let's imagine just the example of a small scalar, 0.1. If you multiply it over and over and over again, you will end up going towards 0 because the value will become smaller and smaller and smaller. And therefore, if theta C to the power of t happens with theta C being very, very small, then we have the problem of vanishing gradients, which we have seen in previous lectures. Now, if the weights are really large, we have the opposite problem. We have the problem of having exploding gradients. Now, this is of course the case in which we would have scalar values. So imagine that we would have just one scalar as a weight, for example. Small weights would lead to vanishing gradient, large weights would lead to exploding gradients. But in our case, theta is actually a matrix, and therefore we have to look at its eigendecomposition to know exactly under which conditions will we have exploding or vanishing gradients. So we're going to look at the eigendecomposition of theta into the matrix of eigenvectors and a diagonal matrix which represents the eigenvalues. And with theta being orthogonal, we can now simplify the recurrence by using the eigendecomposition. Now again, the only thing that we did here was we replaced theta with its eigendecomposition, completely equivalent representation of the matrix of weights of our recurrent neural network. And we can see here how we're going to have this power of t also here in the decomposition. And this is going to be key because once we analyze the recurrence, but with the eigendecomposition, we can now establish that if the eigenvalues have magnitude less than 1, the eigenvalues are the ones that are present in this diagonal matrix, and therefore these are the ones that have the power of t. Therefore, this is being multiplied over and over again. And so now we can establish that if the eigenvalues have magnitude less than 1, we're going to have vanishing gradients, and if the eigenvalues have magnitude larger than 1, then we're going to have exploding gradients. So exactly the same concept as before, as we had with the scalar weights, but with the matrix representation. And so for the exploding gradients, this is not so much of a problem because if we have really large gradients, we can use the technique called gradient clipping. It's a rather simple technique that says, well, if my gradient is larger than, for example, 5, I'm just going to cut it. So any value above 5 is going to be replaced by the number 5. So this is a very simple way of avoiding any damage from exploding gradients. But we have a larger problem if we have vanishing gradients, and we actually have to solve that. But one might wonder, well, I have this recurrent, and I know that if the eigenvalue is smaller than 1 or it is larger than 1, then I have a problem. But why not have a matrix with eigenvalues exactly 1? Right? If below 1 is a problem and above 1 is a problem, why not trying to find the eigenvalues exactly 1? And this is related to the concept of allowing a cell to maintain its state, which will make a lot more sense once we introduce the next few slides. Now recall that vanishing gradients can come from two sources. One is the weights that we have already discussed, but there is another one. Remember that we can also have vanishing gradient coming from the activation function, and especially tanh or sigmoid activation functions. And we already briefly mentioned that recurrent neural networks typically use the tanh activation function. So we're going to have to watch out for that type of vanishing gradient also. At least we can solve the first one by setting the weights to 1, or equivalently in matrix form, setting the eigenvalues to be 1. And this is exactly what this type of recurrent neural networks, long short-term memory networks, or LSTMs for short, this is exactly what they do, setting the eigenvalues to exactly 1 so that we can avoid the vanishing gradient problem and we can train these networks for much longer sequences, hence the name long short-term memory. So let's see how LSTMs are made. So first of all, as we said, the simple RNN has typically a tanh as a nonlinearity. So this is also going to be the starting point for LSTM units. And here we have our representation, which used the inputs xt-1, xt, and xt plus 1, representing this sequence, and our outputs, which are the h's, the ht-1, ht. And here we have an enlarged version of our hidden state A, which now contains this tanh nonlinearity in the middle. And we're going to see how to compose this hidden state for long short-term memory units. So in LSTM, the hidden state is slightly more complicated. So we can see here a depiction of the complete hidden state of the LSTM. But don't be afraid, we're going to go step by step through all of the operations so we can understand what they mean. So now there's a few key ingredients of LSTM units. One of the most important ingredients is this cell. So the cell transports the information throughout the unit. So look at what happens here. This is the cell state at t-1 that enters the current hidden state unit. Some operations are performed on it, and the cell state at ct is the output of this hidden state. So this is sort of a highway for the information, and a highway also for the gradients to backpropagate through this cell state, this highway. And all that we're doing to this cell state is adding some information through multiplication and summing. So this cell state is going to be changed based on the information of the current time step. Now, we're going to have the concept of gates, and gates are going to remove or add information to the cell state. Now, we're going to have these sigmoids that represents the gates, and remember that the sigmoid had output between 0 and 1. And so this is what we're going to do to the cell state. We're either going to multiply it by a 0, erasing all the information, or multiplying by a 1, keeping all the information. So let's look at the LSTM step by step. Let's start with the forget gate. So remember that we had two important ingredients, the cell and the gates. And there are three types of gates, and we're going to start with the forget gate. So the forget gate decides immediately at the beginning here when to erase the cell state. Now, this forget gate is governed in the end by a sigmoid, so the output is between 0 and 1, and it is multiplied to the cell state. So we multiply the output of the forget gate to the cell state. And this means that if the forget gate outputs 0, it's telling the cell state to forget about the information coming from the previous time step. And if it outputs a 1, it's asking the cell state to keep the information. And how does the forget gate decide whether the information should be forgotten or kept? Well, it looks at the input and it looks at the past hidden states. So we have here processing of the input and processing of the previous time step. So all the information coming from the previous time steps is condensed into ht-1, and the information of the current time step is condensed into the input xt. And so this information is processed, and maybe the LSTM realizes that the current time step, the current information xt, has nothing to do with the previous information coming from ht-1. So for example, a completely new activity is starting in the video, and therefore it doesn't make any sense to remember what activity was there before in the video. If this is happening, the forget gate can decide to output a 0, which would completely erase the cell state. Then we have the second gate, the input gate. The input gate decides which exact values are going to be updated. So this is kind of the feature decision, right? It looks again at the input and the previous time steps, ht-1, and it will decide to change the value of the cell state. And this new cell state will be changed according to the output of a tanh function. And remember that tanh outputs values ranging between -1 and 1, and therefore you can subtract or add information to the cell state. And this input gate is going to interact with the cell state with a summation, so adding or subtracting information and updating the values of the cell state according to the input. Now again, what are the operations with which the forget gate and the input gate are interacting with the cell state? So remember that the cell state is kind of this highway for information, right, that is passing along the sequence and that allows us to have this long-term memory. And now we can decide to erase that memory with the forget gate by multiplying element-wise with the cell state. So of course we don't need to forget all the elements of the cell state, but maybe some of the elements. And once this has happened, then the input gate decides with a summation here what kind of information needs to be updated. And finally, you have the output gate. You have the prediction of the hidden state that is going to be passed to the next time step, and that is also going to be used to make a prediction. Now, this is computed by sending the cell state through a tanh, so compressing the cell state into values between -1 and 1, and then having an output gate, which is again governed by a sigmoid, that chooses what values to keep and what values to erase, with this output of the sigmoid between 0 and 1. And so what the output gate is predicting is actually the hidden state at time step t. And this hidden state goes in two ways. First of all, it's used to predict the actual output. So the hidden state at time step t is used to produce the actual output at time step t, and the hidden state is also passed to the next time step so that we know exactly what kind of computations happen during time step t. So we have the cell state that is running at the top, and we have the hidden state that is running at the bottom and that is used directly to predict outputs. Now here we have the formulation of all the elements in an LSTM, all the gates, how we compute the cell update, the actual cell computation, and the computation of the output. Remember that all the gates are governed by a sigmoid function that outputs 0 or 1. The cell update is governed by a 10H. Then we have the interaction between the previous time step and the current time step in order to update the cell. And finally, with yet again another 10H, we take the cell state and we transform it into the output at time step t. And now again, this is a recurrent neural network, which means that all these parameters, all these weights, are going to be exactly the same for each time step and are going to be learned through backpropagation. So how the forget gate decides to forget, or how the input gate decides to change the cell state, this is all learned through backpropagation by tuning all of these weights in all of the gates and even the cell update. So let's look now at the vanishing gradients. Did LSTM solve the vanishing gradient problem? And let's look in particular at how the cell state is updated. It's updated with the forget gate and with the input gate that are interacting with each other. Remember that the forget gate was processing past information, and therefore any recurrence that we have of multiplying the weights over and over again should happen on this side of the equation. So let's look at the first problem we had, vanishing gradients coming from the weights. If we look at the formula, the recurrence that we have is again in the forget gate. And ft are the weights that we're multiplying over and over and over again until we go from ct to c0, time step 0. But these weights are the output of a sigmoid, and they are going to be 1 for important information. Information that we want to keep is going to have a value of 1. And this is how the LSTM essentially sets a value of 1 so that we don't have vanishing or exploding gradients for important information. Let's look at the second problem, vanishing gradients coming from the activation function. The activation function tanh can be found inside this operation. But how this operation interacts with the cell state is through a summation, which means that if there are vanishing gradients in this part, we're not going to propagate them all the way through the cell state. We're just going to keep the vanishing gradients here. And therefore, by having this identity function as this interaction, we avoid having problems from vanishing gradients coming from the activation function. So essentially what we have is very similar to the concept of residual networks, where we had this highway for the gradient to flow, this alternate path for the gradient to flow. This is exactly the same for LSTM. We have this cell state in which the gradient can nicely flow, and we don't have problems of vanishing gradients coming from the weights, nor the tanh nonlinearity, for example. Now, when we're coding an LSTM, we need to decide what is the size of the hidden state. This is going to be the input that we're going to feed into PyTorch, for example, for coding the LSTM. So once we decide that our hidden state has size, for example, 128, then all the other sizes actually have to match. So I need to take my input xt and I need to perform an operation so that my input is squashed or expanded, depending on what's the input size, into a 128 vector representation. So it is very important that all the dimensions match so that we can make the computations, for example, for the cell update depicted here. Now, the cool thing about LSTMs is that we can actually generalize them. So the input, the state, the gates, these are not limited to first-order tensors. We can, for example, have gate functions that are fully connected layers or even convolutional neural network layers. And therefore, we can do architectures like, for example, the conv LSTM, which processes frames in a video sequence. So in this case, of course, our input are images. And therefore, the input, the hidden, and the cell states are all higher order tensors. Therefore, they are all images. So we can even plot what these hidden states and cell states are going to be in the case that our input changes, as we can see here. So in this case, we have the depiction where the input is at the top and we're processing the information, we're outputting the forget gate, and then we have here at the bottom the cell state, which gets changed by the forget gate, by the input gate, and by the output gate. And here we have the hidden state, which is a representation of what is going to be passed to the next time step. So of course, if the input, the hidden, and the cell states are higher order tensors, also the gates need to have convolutional layers, need to be essentially CNNs instead of simple FC layers as we have seen previously. So you can put any type of architecture that you want in there, bearing in mind that this is going to be computationally expensive. Now, recurrent neural networks have often been used in computer vision, for example, for caption generation. So in this case, we already talked about what caption generation is, getting an input image and outputting a sentence that describes the image. Now for this, what we need to have is first of all a feature extraction step from the image, which we do with a CNN, and then an RNN that reads the image, reads those features, and outputs a sentence that describes that image. And we will very briefly talk about what attention is in the next lecture. Now we can also use this, for example, for instance segmentation. So instance segmentation is the problem of identifying different instances of the same type of object. So for example, we want to not only perform person classification, so taking an input image and performing semantic segmentation and assigning to each pixel a semantic label of person, car, and road. But we want to separate the different instances of a particular class. For example, we want to identify different people inside the label person. In this case, in this particular example, we want to enumerate the different leaves that we can see in this image. And for this, again, we can use a convolutional LSTM. Therefore, we use the convolution, the CNN part, to extract features from the image, and we use the LSTM to predict one leaf at a time as if it were a sequence. We are predicting a sequence of leaves. Thank you for your attention in this lecture of transfer learning and recurrent neural networks, and see you at the next lecture.